Welcome to Manufacturing Processes, Machining and Machine Tools lectures by Professor Joyjeet Ghose. This is the 16th lecture of a series of lectures. This lecture will be on milling indexing, part 2. He will be discussing about the types of indexing methods like differential indexing and angular indexing are also discussed with solved examples. In this lecture, solved numerical on differential and angular indexing is also discussed. So, do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access all the videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to this lecture. This is a part 2 of milling indexing lecture. Here we will be discussing about differential indexing and we will be discussing about angular indexing. So what is differential indexing? Differential indexing. Differential indexing is basically a method of automated compound indexing. So here we'll try to divide the workpiece in a number of divisions which is very close to the actual number of divisions that is required. And as we are dividing the workpiece, by moving the indexing crank, there will be a differential movement of the plate as we are trying to divide in the same direction or in the opposite direction. So therefore basically it is adding certain movement to our movement, or it is subtracting certain movement to our movement. So try to imagine if the hand of the clock is moving in clockwise direction, and simultaneously if the body is the dial is also moving in clockwise direction. So will it take more time or less time to complete, let's say 10 minutes, or move from 1 to 2? So how much time it will require? So for 1 hour, will it require 1 hour or will it take more than 1 hour? And similarly, if the dial moves in opposite direction, so how will it take more than 1 hour or will it take less than 1 hour to reach from 1 to 2? So you know the answers. Obviously, if it is moving in opposite direction, it will take less time. If it is moving in same direction, it will take more time. So we are adding certain moment and we are subtracting certain moment. So similarly, it works in differential indexing. It works in that manner. So let's discuss the components used in the construction of the setting that is used in differential indexing. So this is the worm wheel on which this spindle is mounted, and this is the worm. This is the worm which is mounted on this shaft. So worm messes with the worm wheel. Worm wheel has 40 teeth, and this worm wheel carries the spindle, and the spindle the workpiece is mounted. So it is mounted here, and the index crank is mounted on the this shaft, same shaft. This is the same shaft, and independent of this is the slip on which the index plate is mounted. So and there is a pin, locking pin here. So before you start differential indexing, this locking pin has to be freed. That means the index plate should be freed. So now this free index plate has a bevel gear on it, on the slip. This bevel gear messes with another bevel gear, which is the pinion bevel gear. Pinion bevel gear has a shaft here, and it has some bevel gears on it, and these are the gears fitted to this shaft. So here, as we are trying to rotate, the index crank is rotating, the worm is rotating, the worm wheel will be rotating. As the worm wheel rotates, the workpiece will also rotate. Also, the worm wheel shaft or the spindle shaft has a driver gear. So this driver gear will also rotate. This driver gear will drive these driven gears, and simultaneously the bevel gear will rotate, and this bevel gear will drive this bevel gear, and this bevel gear, when it rotates, this will also rotate. The index plate will also rotate. So what is happening here, as we are trying to index, the plate is also rotating in the same direction or in the opposite direction. That will depend on the change gears. Now here at this point, if you are not aware of simple gear train and compound gear train, please Google it and study simple gear train and compound gear train. Then only you will be able to understand what is a differential indexing. I am not going to explain the simple gear train and compound gear train at this point of time. So if you don't know, get some knowledge of it and then come back and watch this video. Okay, so this is what happens actually. Now point is that what should be the type of gear ratio, we have to find it out for a particular divisions that is required. So that requires the mathematics of it, and the formulas are given here. And okay, so a universal dividing head comes with a set of gears. This set of gears are given to us, this much gears having 24 teeth, 28 teeth, 32 teeth, 40 teeth, 44. So with this number of gears, we should be able to divide the workpiece any divisions from 1 to 382 divisions. So some more gears are required. So with this we are able to divide the workpiece in 382 divisions, and further to divide more than that you will require some extra gears also. So with this we move on, and these are the steps that is given to us. Okay, so in the first step we'll select A. Now while selecting A, in order to find out the gear ratio, the gear ratio will be A minus N into 40 by A. Now we have to select A. The first step is to select A. A is a number which is close to the divisions that is required. That means A is very close to N, and A can be simple indexed. A can be simple indexed. Okay, the A is a number. Suppose we want to divide the workpiece in 97 divisions. Let's say we have taken A as 100. Now it is not necessary that A should be more than N. A can be less than N also, and this can be negative. If it is negative, ignore the negative sign, we'll take the mode of it. So A can be more than N, A can be less than N, but A should be very close to N, and A should be simple indexed. Okay, so with this we'll find out the gear ratio. This gear ratio that we'll find out will be from the set of gears that is available. We cannot select any gear having any number of teeth. We are limited to the number of teeth that are available to us. So once we have found out the gear ratio, the driven and the driver gears, and the type of gear train, then we'll move on to the second step. What will be the index crank movement? The index crank movement should be 40 by A. That means if you are selecting, let's say in our case 97 divisions, we have selected A as 100. That means 40 by 100, and this will be repeating how many times? 97 times. This will be repeating, this index crank movement will be repeated 97 times, but we are trying to divide the workpiece in more number of divisions, right? We are trying to divide the workpiece in more number of divisions. We are trying to divide the workpiece in more number of divisions. So a differential movement should be added to it so that the number of divisions decreases to actual number of divisions will be 40 by N. So try to understand this movement, differential movement. So in step 3, we have to find out the change gears. So these are the change gears depending on the type of gear train that is available. Right now probably it is not, you will not be able to understand it. If the gear train is simple and M minus N is positive, that is if A is greater than N, then only one idler gear is used. One idler gear is used. If M minus N is positive, that means that the plate must move in same direction. That means we have to add a certain moment. Okay, if you rotate in opposite direction, we have to subtract certain moment. Okay, so accordingly we have to calculate the idler gears. What idler gears? Again, we have to know about gear train. So this is the mathematics of the formula that we have calculated here. You can go through it. I'm not going to discuss this. So we'll start with a problem. So this is the 87 divisions we have to divide. Same problem we have done for compound indexing also. And here the change gears are given to us. The first step is to find out the gearing ratio. This is the gearing ratio we have to find out, and we have taken A as 97, 87. So A I have taken 90. A I have taken as 90. Now this A can be simple indexed, because this 90 can be simple indexed. 40 by 90 is 4 by 9. That means 12 holes in 27 hole circle of B and S plate number 2. Sorry, it should be plate number 2. Is an error here. It should be B and S plate number 2. So therefore I can take A as 90. So calculating the formula, 90 minus 87 by 90, this we get 4 by 3. Now 4 by 3 I can multiply by 8, and both numerator and denominator 8, we get 32 by 24. So 32 gears is available and 24 gear is also available. This is a simple gear train. So driver is 32. 32 number teeth will be fitted to the spindle, and 24 number teeth will be fitted to the bevel gear shaft, bevel gear pinion shaft. Okay, and this is a simple gear train, and a minus n is positive, so only one idler gear has to be added. One idler gear has to be added because you want to rotate the index plane in the same direction. If two simple gear train is added here, if two gear is added here, if this is two gears, if this rotates in this direction, this will rotate in this direction. One is anti-clockwise, this will be clockwise, so you don't want it, so you want it in this direction. So this is idler, driver, this is driven. Okay, so the next plate, 241 divisions. Similar thing will be following here. We'll take A as 240. A is 240 because I have taken, because A can be simple index here. You can see A 40 by 240 is 1 by 6, that is 3 by 18. So 3 by 18 holes, 3 holes in 18 hole circles in plate number 1. And so if A is 40 to 40, then we get it as 1 by 6. So 1 by 6 can be 1 by 2 into 1 by 3. And so this ratio is to be maintained 32 by 64 into 24 by 72. So this is a compound gear train. The drivers are 32, 24, 64, 72. It is somewhat like this. A compound gear train will be somewhat like this. In the same shaft, 32, 24. This is 32, this is 24. Okay, sorry, very sorry, extremely sorry. 32 matches with 64. This is driver, this is driven, this is 64. On the same shaft we have 24 masses with, this is 24, this is here 72. So here this direction and this direction will be same because in between we have a shaft. Therefore no idler gear will be required if A minus n is positive. But in this case A minus n is negative, so therefore we have to use another idler gear here, somewhere around here or between here. So that will change the direction of rotation. So this is the problem that we have discussed. I think we have discussed 2 points, 2 problems. If you have any doubt regarding this, if you are not confident in simple gear train and compound gear train, so please go through that. Okay, there is another combination that is possible is 24 by 48 and 24 by 72. So basically this gear ratio has to be maintained, and any gear train in gears you can use so long as the number of gear teeth are available in the set of gears. That's up to you. I hope differential indexing is clear to you. Let's move on to this is another problem, 83 divisions. I'm just okay, there is another here. It's compound gear train. Drivers are 72 and 40 and drivens are 24 and 86. With this we move on to the angular indexing. Solution 2. This is solution 2 and this is solution 3, the same problem. A problem may have multiple solutions. Okay, angular indexing. So angular indexing is basically dividing the workpiece in angular measurements. So we know if we rotate the crank by certain angles, the workpiece will move by certain angle. So there are 360 degrees in a circle. So when the index crank is rotated by 40 number of divisions, the spindle rotates through one complete rotation by 360 divisions. Therefore, one complete turn of the crank will cause the work to rotate 1/40th of rotation, that is 360 by 40 is equal to 9 degrees. So if you rotate the crank one time, the workpiece will rotate by 9 degrees. So with this knowledge, and if you in minutes it will be 540, and in seconds it will be 32,400. So accordingly, this will be the formula, angular displacement of the work in degrees, and these are some of the examples. The crank movement for 60 degree angular will be 60 by 9, that is 6 by 9. So 6 into 2 into 9 into 2 will be 6 complete rotations and 12 holes in 18 whole circles. Likewise 35 degree, 35 by 9 is 8 by 9. So that is basically 3 holes and 24 holes by 27 whole circles. Okay. So likewise we can divide in seconds also. The angular division is 34 degree and 12 seconds, 12 minutes will be 34 into 60 plus 12 will be 2052 minutes. That will be 2052 by 540, that is 312 by 15. That means 3 complete rotations and 12 holes in 15 whole circles will divide the workpiece in 34 degree and 12 minutes. So I hope the differential indexing and angular indexing is clear to you. Any doubts, if you have, you can contact me or put it in the comment box. Thank you for watching this video.